The Spark, the Crisis of the Ether, expanded narrative. Before the great rupture in our understanding of space and time, physics rested upon a comforting assumption, almost like a hidden philosophical pillow upon which the mind of the 19th century lay at rest. It was believed that light, like every other wave known to science, must have a medium through which it travels. Water carries waves upon its surface. Air carries sound through its vibrations. And so, naturally, the universe itself was assumed to be filled with a subtle, invisible substance, the luminiferous ether. This ether was not merely a scientific hypothesis, it was a metaphysical necessity for many thinkers. It had to be everywhere, filling even the emptiest vacuum, because how else could light cross the vast emptiness between the stars? To the physicist of that era, the idea of nothing carrying something seemed absurd. A wave without a medium was like a ripple without water, an effect without a cause. Maxwell's equations, which unified electricity and magnetism into a single elegant framework, strengthened this belief. When James Clerk Maxwell derived the speed of electromagnetic waves, he found something astonishingly precise. In the vacuum of space, the speed of light emerged not as a mysterious measurement, but as a consequence of two deep properties of nature. C, Jai frac 1 Ramu 0 over epsilon for R0 dal. Here, Ramu 0 represents the magnetic permeability of free space, and var epsilon Ras 0 represents the electric permittivity of free space. This equation whispered something profound. Light was not random or mechanical, it was woven into the very structure of electromagnetism itself. Yet even this elegance did not dissolve the belief in the ether. Instead, it strengthened it. Scientists began to imagine that these constants, mu tharo and var epsilon tharo, were properties of the ether itself, numerical fingerprints of an invisible ocean filling all of space. In their minds, Maxwell had not eliminated the need for a medium. He had only described its properties with mathematical precision. And so, a grand expectation took hold. If Earth is moving through this ether, much like a ship moving through water, then there must be a detectable ether wind. Light traveling in the direction of Earth's motion should behave differently from light traveling perpendicular to it. Its speed, measured relative to Earth, should vary slightly depending on direction. This was not a minor prediction. It was a cornerstone of how physicists believed reality must behave. To detect this subtle difference, one had to imagine the Earth as a moving observer through a stationary cosmic fluid. If you move forward while light moves against your motion, the effective speed should be slightly altered. Conversely, if light moves sideways relative to your motion, the behavior should differ in a measurable way. This expectation was not considered speculative, it was considered inevitable. The idea of motion itself was still deeply rooted in Newtonian intuition. Space was absolute, time was universal, and somewhere in the background, the ether provided a fixed reference frame, a cosmic stage that defined true rest. Even the most sophisticated equations of motion were silently anchored to this unseen structure. Thus, physics entered the late 19th century with a quiet confidence. The ether was not just possible, it was necessary. Without it, the very wave nature of light seemed to float without grounding. But beneath this confidence, a subtle unease had begun to grow. Experiments in optics and electromagnetism were becoming more precise. Instruments were becoming sensitive enough to detect even the smallest discrepancies in the speed of light. If the ether truly existed, it should eventually reveal itself, not through philosophy, but through measurement. And so the stage was set for one of the most delicate confrontations between expectation and reality in the history of science. A confrontation not between competing theories alone, but between the imagination of what the universe must be and the quiet testimony of what it actually is. The world believed it was about to detect the breath of the ether. Instead, it was about to discover something far more unsettling, that the universe might not require a medium at all, and that light, unlike anything else known in classical physics, might obey rules that belong to a deeper structure of reality itself. The logic, the Michelson-Morley experiment, the failed detection. If the idea of the luminiferous ether was the philosophical expectation of an orderly universe, then the Michelson-Morley experiment was the moment reality was asked very politely to confirm it. It was not a reckless experiment. It was a masterpiece of precision, patience, and intellectual courage, designed to detect something so subtle that even failure would become revolutionary. The reasoning was simple in its elegance. If Earth is moving through a stationary ether, then light traveling in different directions relative to that motion should not behave identically. There should be a measurable difference in the time it takes for light to travel in one direction compared to another. To capture this idea, Albert A. Michelson and Edward Morley used a device known as an interferometer. At its heart, it was a careful comparison of two beams of light, split, sent in perpendicular directions, and then recombined. If the Earth was moving through the ether, one beam would effectively swim upstream, while the other would move across the current. Even if the difference was extremely small, it would reveal itself as a shift in interference patterns. Let us imagine the Earth moving with velocity, v, through the supposed ether, while light travels at speed, c, relative to that medium. Consider first the beam traveling in the direction of motion. The effective speed of light in that direction would be expected to behave like pi t parallel pi c v quad on text forward direction dot, and in the opposite direction c text back pi c pi v quad r text return direction. For the perpendicular beam, the situation is more geometrically subtle. The light does not simply go sideways in a straight classical sense because the apparatus is moving while the light travels. Instead, one must use the Pythagorean relationship to account for the diagonal path. This leads to an effective speed reduction described by geometry rather than simple subtraction. Michelson realized that if the ether exists, the time taken for light to travel back and forth along the parallel arm would be different from the time along the perpendicular arm. Let us denote the length of each arm as LE. For the parallel direction, the total round-trip time would be expected to be T parallel frac L C V pa frac L C pas by phi. If we combine these fractions carefully, we obtain T parallel half frac 2 LC C2 V2 I. Now, for the perpendicular direction, the calculation is more geometric. Because the apparatus moves while light travels, the light must trace a diagonal path. The effective round-trip time becomes T V perp and shaksh na frac 2 ISQRT C2 V2 IR. At this stage, the expectation becomes clear. If T parallel NQ T per pla, then a measurable shift in interference patterns should appear when the apparatus is rotated. This shift would be tiny, but not zero. Michelson and Morley were not searching for drama, they were searching for precision. To quantify the expected effect, physicists defined a time difference, Darwin delta, T referring T parallel C T per lar. This time difference should translate into a shift in interference fringes, observable as a movement of light and dark bands when the apparatus is rotated by 90 degrees. But the experiment revealed something profoundly unsettling. No matter how carefully they rotated the apparatus, no matter how precisely they controlled temperature, vibration, or alignment, the expected shift simply did not appear. The interference pattern remained stable. The value of R delta T was effectively dar delta T approx 0 dar. This was not a small discrepancy. It was not experimental noise. It was a silence where a signal was supposed to exist. The ether, which was expected to produce directional differences in the speed of light, left no trace. The equations predicted motion through a hidden medium. The experiment reported no such motion at all. Light behaved as though there were no preferred frame, no hidden wind, no cosmic fluid resisting or assisting its journey. The beauty of the Michelson-Morley experiment lies not in what it confirmed, but in what it refused to confirm. It took one of the most deeply held assumptions of classical physics and exposed its absence, not with argument, but with measurement. In that absence, physics encountered a question it was not prepared for. If there is no ether, then what exactly defines the speed of light as constant in all directions? The experiment did not answer this question, but it ensured that no serious physicist could ignore it again. The core, Einstein's radical interpretation, the universe without ether. There are moments in the history of thought when the solution to a problem is not found by adding something new, but by daring to remove what everyone believed was essential. The Michelson-Morley experiment had already whispered a disturbing message. The supposed ether wind could not be detected. Yet many physicists of the time tried to rescue the old worldview by introducing increasingly complicated hypotheses, contractions, hidden motions, compensating effects, anything to preserve the idea of a privileged medium filling space. But the deeper question was not how to save the ether. The deeper question was whether it was ever needed at all. In this intellectual atmosphere, I arrived at a simple but unsettling thought. What if the speed of light does not depend on any medium whatsoever? What if light is not a wave carried by something else, but a self-sustaining structure of nature itself? This idea did not arise from experimental persuasion alone, but from a philosophical demand for consistency. The laws of physics, if they are truly universal, should not privilege one observer over another merely because of uniform motion. If two observers move at constant velocity relative to each other, neither should be able to claim absolute rest. This principle became the first cornerstone. The laws of physics are identical in all inertial frames, but this alone was not enough. The second, more radical pillar was needed. The speed of light in vacuum is constant for all inertial observers. This statement appears simple, almost innocent, but it quietly dismantles the entire architecture of Newtonian intuition. To understand its depth, imagine two observers. One stands on Earth, another moves smoothly in a train at constant velocity. Classical reasoning would insist that if a beam of light is emitted forward, the moving observer should measure a different speed depending on their motion. Velocities should add. This idea is captured in the classical transformation. Plus u attribute for u, beta where u is the speed of light in one frame, v is the relative velocity between observers, and u is the observed speed in another frame. But nature refuses to obey this rule when it comes to light. Instead, every observer, regardless of motion, measures. So we see 29999, 792, 458, text and does. The constancy of IC is not a result of measurement error. It is a structural feature of reality. This immediately forces a profound consequence. If velocity does not transform in the classical way, then space and time themselves must be more flexible than previously imagined. To preserve consistency, I introduced a new transformation law between inertial frames. Let one observer measure coordinates x, t, and another moving at velocity v along the x-axis measure x, t. Instead of the classical Galilean transformation, a new structure emerges, x, no gamma, x, vt, ta, t, ya, ha, gamma, ha, left, t, no, frac, fix, and 2 to right, where the factor ta, gamma, ta, frac, 1, court 1, frac, by 2, high 2, is not a correction. It is a gateway to a new geometry of reality. This factor, R gamma, known later as the Lorentz factor, reveals something extraordinary. As velocity, v, approaches the speed of light, c, the denominator approaches 0, and thus, an gamma right arrow infinity. This means time and space do not remain rigid backdrops. They stretch, contract, and transform depending on relative motion. From this framework, one of the most striking consequences emerges. Time itself is not universal. A moving clock ticks differently compared to a stationary one. This is expressed as Dorringer delta T gamma R delta T dollars. Time is no longer an absolute river flowing identically for all observers. It becomes a relative experience shaped by motion itself. Similarly, lengths contract along the direction of motion. Space and time, once thought to be separate and fixed, now reveal themselves as intertwined aspects of a single structure. This unified structure is what I later called space-time. The most profound shift, however, is conceptual rather than mathematical. The ether was unnecessary because it assumed a preferred rest frame, a cosmic stage against which all motion could be measured. But if the speed of light is the same for all observers, then no such privileged frame exists. Every inertial observer becomes equally valid. Motion becomes relative, not absolute. Space and time lose their independent meaning and become coordinates within a deeper geometric reality. Thus, instead of asking, through what does light travel, we must ask a more subtle question. What is the structure of reality that enforces the constancy of light's speed? The answer is not a medium, but a symmetry, a deep invariance of the laws of nature. In removing the ether, we did not remove substance from physics. We removed unnecessary assumption. And in doing so, we uncovered something far more elegant, a universe where space and time themselves participate in the dynamics of reality rather than merely hosting them. This was the true beginning of relativity, not as a modification of classical physics, but as its complete reimagination, the ripples, the birth of special relativity, space and time, rewritten. Once the idea of a constant speed of light is accepted as a fundamental law of nature, the universe can no longer remain the quiet, rigid stage imagined by classical physics. Something deeper must give way, not matter, not energy, but the very framework in which all events occur, space and time themselves. Before this realization, physicists believed in a simple structure of reality. Space was absolute, a fixed three-dimensional container, and time flowed uniformly for all observers, like a universal clock ticking across the cosmos. In this worldview, two events separated by time, t, and space, x, were understood independently as though they were unrelated dimensions. But once light refuses to obey classical velocity addition, the structure begins to crack. The constancy of ICE demands that no observer can detect absolute motion. And if no absolute motion exists, then there can be no absolute space or absolute time either. To see the depth of this transformation, we begin with the most profound geometric idea in physics. The separation between events is not purely spatial or purely temporal, but a combined entity known as the space-time interval. This interval is defined as space 2 times y, c times 2, t times 2, x times 2, y 2, z times. That is, this equation is not merely a measurement, it is an invariant. It means that while different observers may disagree on t, x, y, and z, they will always agree on S2. Reality, therefore, is not built from space alone or time alone, but from this deeper structure that remains unchanged under transformation. To preserve this invariance, space and time must transform together. This leads naturally to the Lorentz transformations, time x in gamma, s of et, times gamma left, t and frac x, right, side with dal gamma frac and s car 1 frac tan 2 psi 2. These equations reveal something astonishing. Time is not separate from space. It is influenced by motion through space. Similarly, space is not independent of time. It bends depending on temporal separation. From this structure arises the first great consequence, time dilation. A clock moving at velocity, v fa, does not tick at the same rate as a stationary one. If delta t is the time interval measured in a stationary frame, the moving observer measures tau. Delta t far plus gamma r delta t tau. This is not an illusion. It is a physical reality confirmed by countless experiments. Time literally stretches for moving systems. The faster one moves through space, the slower one moves through time. The second consequence is length contraction. An object moving at velocity, v, along its length, L, is measured to be shorter in the direction of motion, till L and frac L, gamma, till. Thus, space itself contracts depending on motion. What appears as a fixed rod in one frame becomes a shortened structure in another. These two effects are not independent curiosities. They are necessary consequences of preserving the invariance of the speed of light. Times C Chernashu, frac R text, distance, text, time. If all observers must measure the same, CE, then either space must shrink or time must stretch, or both must adjust in a coordinated way. Nature chooses consistency over intuition, but the most profound shift is not in these formulas, it is in what they imply. Space and time, once thought to be separate entities, merge into a single four-dimensional continuum, space-time. In this framework, an event is not defined merely by where it happens, but also by when it happens. An event is described by coordinates, dollars, x, y, z, t. But these coordinates are not absolute truths. They are perspectives, different slices of the same underlying reality depending on the observer's motion. Even velocity itself becomes relative in a more subtle way than classical intuition allows. Instead of simple addition of speeds, velocities combine according to UK frac U pause V1 pause frac of C2 dollars. This ensures that no matter how velocities are combined, the result never exceeds c. The speed of light becomes not just a constant, but a cosmic speed limit embedded into the structure of spacetime itself. The universe, therefore, is not built from rigid space filled with moving objects. It is a dynamic geometric fabric where motion reshapes the very coordinates used to describe reality. From this perspective, gravity itself, though not yet fully revealed here, will later emerge not as a force, but as curvature within this space-time structure. But even at this stage, the transformation is already complete. Absolute space and absolute time have vanished. What remains is a universe where every observer carries their own valid version of space and time, and yet all are connected through the invariant structure of space-time intervals. The ripples of this discovery extend far beyond equations. They reach into the deepest assumptions of human intuition. We are no longer observers in a fixed arena. We are participants in a flexible, interwoven geometry where motion shapes reality itself. And in this realization, physics does not lose simplicity. It gains a far deeper elegance, one where the universe is not described by what changes separately, but by what remains invariant beneath all change.